Today, we want to talk about parameterized curves. The big idea is that we want to be able to describe one-dimensional curves in R3. Think about what we've been doing before. We started off describing surfaces in R3. And that was convenient because if we write one coordinate as a function of the other two, for example, z equals f of xy, that frames things in terms of functions, which we like. We always start with the simplest case where one coordinate is a function of the others. And that produced a two-dimensional surface in R3. Then think about what we just finished describing with our double and triple integrals. The big work behind setting up a double integral is not the integration part. We already know how to do that. The big work in the double integral is describing the region for the integral so that the integral can understand what values we want to plug into the function, because that's all we're doing with the integral, plugging a bunch of values into the function and adding them up. Same thing with triple integrals. The focus was not on the integration part. We already know how to add one to the exponent and divide by the new exponent. We already know how to do trigonometric substitution. The point of the section on triple integrals was describing three-dimensional solids to be the collection of points that we plug into a function of three variables. Our big job right now is describing stuff. One of the stuff that we want to describe is one-dimensional curves in R3. We know that writing one coordinate as a function of the other two will result in a two-dimensional surface. If I write z equals f of xy, or x equals g of y and z, or y equals h of x and z, I think I got those three, then we'll end up with a two-dimensional surface in R3, like a big curvy sheet of paper in the room. But we might want to analyze derivatives and integrals along a one-dimensional curve in R3. Perhaps like a curve with a fly flying around the room. The path that it traces out is not going to be a surface, it's going to be a curve, one-dimensional. And there might be some information about that path where we would want to do some derivative stuff, analyze the direction at a given point, or some integral stuff, add up a bunch of values along that curve. To this end, we're going to define x, y, and z independently of each other and write them all as functions of some parameter, which is usually t. So the points on the curve are x of t, y of t, z of t. And then this would be for some range of t values, some interval of t values. So the interval t goes from a to b. These are the values of t that we plug into each of these three functions. So each of those values of t we plug into the function, and that gives us a coordinate, and that's where we get the curve. Cool stuff happens when we do this. Let's first look at the example that we always look at in every calculus book ever when it first starts, before we even think about R3. It's crazy. I always admonish students for not treating math as case sensitive and using capitals when instead of lowercase, but I always write capital pi. Some habits are hard to break, I guess. So here's a nice classic example. X of t is 3 cosine t, y of 3 is 3 sine t. For t between 0 and 2 pi, this will produce a circle of radius 3 centered at the origin. So this is going to be a circle of radius 3 centered at the origin. But moreover, we get more things when we parameterize it. We start by plugging in 0 and we stop by plugging in 2 pi. So by defining this range of values for t, we are also getting a start, a direction, and an end. So this graph is going to start at 3, 0. And moving, in this case, counterclockwise. So we're getting additional information. We're assigning some direction to it. We're saying starting at 0, when t is equal to 0, we start at 3, 0, and we go once around the circle counterclockwise. We can watch this happen on our calculating machine. So we have to tell the calculator that we want to do parametric equations. So we have to go into our mode and drop down from and change from function to parametric. When we're in function mode, in the y equals screen, the calculator will only accept function y as a function of x. We can't even switch it around. X is a function of y. We have to do y as a function of x. Secretly, we can. We just be like there. So we want to try to do some parametric stuff. So we'll go into the mode and switch from function to parametric. Now, when I hit the y equals screen, each graph has 2 inputs. I have an x function and a y function. So x1 of t and y1 of t. So I want x equals 3 cosine t and y equals 3 sine t. I want to tell the calculator to plug in values from 0 to 2 pi. So that's going to be in my window. My window the first thing is going to be t minimum, t maximum. There's 0 to 2 pi. And then the t step is just going to be how often we want to plug values in. Then the rest of it is traditional window. X min from negative 6.6 to 6.6 and y min to y max of negative 4.1 to 4.1. So let's hit the graph and see what we get. So we get the circle of radius 3 as advertised. But moreover, instead of just getting, instead of just having the circle started off at 3, 0 and went counterclockwise once around the circle. We can adjust how much of the circle that we get by changing the values of t that we plug in. If I only plug in the values of t from 0 to pi, we only get half a circle. If I want the bottom half of the circle, I could put in values from pi to 2 pi. That gives us the bottom half of the circle. If I want the right half of the circle, then I could go from negative pi over 2 to pi over 2. It makes sense that this is going to give us a circle of radius 3 because x is cosine and y is sine. And we know the equation for a circle of radius 3 is x squared plus y squared is equal to 9. If I plug in these functions for x and y, so 3 cosine of t squared plus 3 sine of t squared, we're going to get 9 cosine squared plus 9 sine squared. If we factor out the 9, we have 9 times cosine squared t plus sine squared t. Cosine squared plus sine squared, that's our favorite Pythagorean identity. That's just 1. So it looks like everything checks out. It's good that these descriptions are interchangeable. Otherwise, something would be horribly wrong. At this point, we might notice that there's nothing special about cosine squared plus sine squared versus sine squared plus cosine squared. So what if we switch the roles of cosine and sine? What if I, just based on this equation business, if I define x as sine and y as cosine, for t between 0 and 2 pi. Just based on the previous work, we should get a circle of radius 3 centered at the origin. Let's find out what happens. So if I switch the roles, we know we're going to get a circle because the x squared plus y squared equals 9. That makes a circle. These values of x, these functions x of t and y of t also fit that description, just like cosine sine. So let's watch what happens. Oops, let's change our window back to 0 to 2 pi. So we still get the same circle, but it started somewhere else and it went in the opposite direction. So that's cool. So it's a circle of radius 3, but instead of starting at 3, 0, this one started at 0, 3. And this time it moved clockwise once around. So that's pretty cool. We can also notice that we've got this, this was 3 sine t and 3 cosine t. The coefficients of both of those were the same. And that's where, when we plugged into x squared plus y squared equal 9, I had a 9 cosine squared plus 9 sine squared. And I was able to factor out a 9 and get this cosine squared plus sine squared. That was equal to 1. What if I change one of those values? So for example, what if I change x of t, instead of 3 sine t, I change it to 4 sine t? And let's put y of t at the same. Y of t is going to be 3 cosine t. And let's still go for t between 0 and 2 pi. So I just want to change this 3 to a 4, and let's see what happens here. Think about it for a second. Make a guess, and then press graph to see what happens. Looks like it's squashed out a little bit. And notice that the left and right ends are no longer at 3, but they've been pushed out to 4 and negative 4. So we're getting an ellipse with a major axis on the x-axis, and that radius is 4, and the minor axis on the y-axis, and that radius is still 3. So we end up with an ellipse just a squash circle. Moreover, the 3 still shows up. We still go from 0, negative 3 to 0, 3 on the y. But now our left and right, or our right and left, is 4, 0 and negative 4, 0. I didn't change the sine versus cosine. X is still on sine and y is on still cosine. So in this case, we started at 0, 3. And we went clockwise once around. So we were moving in this direction. To make it fit with what we did before, what if I change x back to cosine and y back to sine? We should speculate that we'll still get the same ellipse, but now we'll probably start at 4, 0 and move counterclockwise once around. It's like I've done this before. But we went back to the original setup. I just fattened up the circle so that on the x-axis, we go from negative 4 to 4 rather than from negative 3 to 3. Questions? Yeah, by switching x of t to sine, we ended up going clockwise. We also started off at 0, 3 instead of 4, 0. Now, this was just being able to describe these directions as clockwise versus counterclockwise. That works because we pick things that would just go around once. T goes from 0 to 2 pi, everything just goes around once. The important thing to note is that by parameterizing our curves, we're assigning a start and an end and a direction. We're assigning a direction to the curve. when we parameterize a curve, we give the curve direction. That's the important thing to take away. So in the fly example, when we map the fly going across the room, we come up with functions for its x, y, and z coordinates at any given time t. It started off when t is equal to a and ended when t is equal to b. If we want to reverse that, we could just go from t equals b to t equals a, and that would reverse the direction of the fly. So whatever the curve is doing, so in this case, we had clockwise and counterclockwise. We just start off at a point when t is equal to a, and then the point winds through space and ends when t is equal to b. So we've assigned a direction to the curve. So we're moving from a to b. It's not just a path. We're moving in a direction. So you might be thinking, gosh, with all this stuff in three-dimensional space and the word direction being used, are vectors going to show up? Of course. I use the word direction. This is a math class. Vectors are absolutely going to show up. What kinds of things are we going to do with this curve once we're able to parameterize it? That's just a case of what kinds of things do we do in calculus? Derivatives mean find the slope of the tangent line, or find what direction are we going at a given point. Integrals just add up a bunch of values for the function. So if I call this a curve, this is some curve C, I'll have some function. This is this curve. The points on this curve will be the points that we want to plug into the function. So we would be able to do something like, let's plug in all the values on this curve into this function for some small change in t. Take all the points on the curve, plug them into the function, and add those up. Because that's what we do in integration. Derivatives, what direction are we going at a point? Integral, we're just adding up a bunch of values of the function. Any questions? This is why third semester calculus is best semester calculus. We can finally start to see bigger pictures. It's really weird when when in single variable calculus, when we're plugging in a bunch of values into the function. They always come from the same boring place, an interval, start at A, end at B. Once we get into functions of more than one variable, now we have lots of different points that we want to plug into the function. And now it's interesting to describe them. As far as integrals, integrals can represent whatever we use integrals to represent. Mathematically, what we're doing is adding up a bunch of values for the function. One of the things that we use integrals for is to calculate distance if our function is velocity. So that's a great question. What are these integrals going to represent? They're going to represent anything that we can represent with integration in general, which is anything that we can represent with multiplication, which is anything that we can represent with addition. So remember, there's not some magical connection between integration and coming up with the distance traveled. That problem was just convenient for us. But that problem still comes down to our t-axis being a function of time and our vertical axis being a function of speed. And so our function is in meters per second. And so our area is in meters per second times seconds. And so our when we multiply meters per second times seconds, the seconds cancel and we just get a result in meters. So there's nothing magical about it. It's just that's the thing that we used it for. If our function happens to represent force, and our t happens to not represent seconds, but distance, then when we do f of t times delta t, we have newtons times meters. F of t delta t is in joules. Nothing special about distance and integration. It's just that's our go-to because it's the first one that we start using because distance is equal to rate times time. Any questions? Comments? Deep thoughts? Cool. Remember, the point of going to school is not to answer all of your questions, it's to raise more questions. You need to graduate with more questions than you matriculate with. Otherwise, something went horribly wrong. I mean, along the way, hopefully some questions get answered, but answering some questions should only lead to more questions. If at any point you feel like you've got all the answers, you need to be cut off from society. Wow, that's just no. Because you're going to become set in your ways and you're going to start thinking things like, this is the way, everybody should just do it this way. And that is very unhealthy. You also need to square yourself with the fact that you can't know everything. There's too much to know. And then think about how horrible it would be to actually know everything, have no more mysteries. Every bit of curiosity has been satisfied. What would be the point? The only true knowledge is knowing that you know nothing. Because if there's an infinite number of things to know, it's not, and you just only can know a finite amount of stuff. When you compare finite to the infinite, it's zero. So revel in that and learn as much as you can, or despair at that and quit. You know what I mean? I hope, since you've chosen optional education, so-called higher education, since you've chosen this optional education, my hope is that it's the former. You revel in this not knowing things and you push to find out. Not because eventually you'll know everything, but because eventually you'll just know more. And hopefully that's enough. It's my usual advice for students that think they want PhDs. If you want to get a PhD, it's not even going to be a question about whether you get your PhD. That has to come from inside, that you're going to get your PhD because you have to do it. If someone is telling you to get your PhD and that's the reason that you're doing it, you're never going to make it. PhD has to come from you. You have to get your PhD because you have to get it, not because anyone else thinks you should. You can externally get yourself through a bachelor's degree. You can get through a bachelor's degree based on external pressures, I believe. I think you get less out of it, but I think it can be done. I'm pretty sure that you can pretty much get a master's degree based on external factors. Well, my family wants me to get my master's degree, so I'll do that. But once you get to the PhD level, you can't do that for someone else. Even if you've done it, it's not going to be the same experience. You're not going to get out of it what you could have gotten out of it. And then it becomes a loss of time and money. Money, whatever. Time, can't get it back. You know what I mean? All right. Enough of this silly nonsense. We're describing curves in space. Think about the things that we're going to do once we have this is just a collection of points and a direction, but just a collection of points. We're either going to figure out what direction things are headed at a particular point, derivatives, or we're just going to add up a bunch of values for this function, integrals. That's going to do it for today. I will see y'all on tomorrow. Everybody have a good day. And thanks for playing.